All right. Hello, everybody. Welcome to Chemistry for Engineers. Okay. We'll be using the Chemistry for Engineers 4th edition by Brown and Holm. I'm Jennifer Termel at SMCC, and you'll get to know me this semester. I have a master's degree in chemistry, and I worked as a process engineer for 2 different semiconductor companies. So I really enjoy teaching this class. You can use a 2nd or 3rd edition textbook as well. So you can go ahead and get those used if you want a hard copy. There is also a bootleg copy of the 2nd edition floating around the internet in PDF form, and you are welcome to hunt that down as well. So we will get started. Okay, so first of all, let's go ahead and take a look at these chapter objectives. Now, before I go any farther, let's actually go take a quick look at something else. Okay, let's actually, hello. We're going to come here. All right. And I'm going to tab over to this other tab. Okay. So you can see right here that what we are looking at is your notes template. Now, this is in Brightspace. Okay. You will be, and I will hand it out in class as part of a packet. But if you're working through this before chapter 1, or perhaps you missed a class and you didn't get a chance to pick up the packet, please print this out, as you can see here, and fill it in as we are doing lecture. It's part of your homework, and I will be collecting it with your I will be collecting it with your homework packet as well. Okay, so that's kind of the point of a flipped class. You're going to be watching these videos and taking notes on here, and then in class we'll be working through problems. And this tends to work really, really well because students can do the learning on their own time and they don't have to be in lecture. Okay, so let's come back to the slides and let's take a look here, and let's just go through a few things. You'll notice these are the chapter objectives, and these are all on your sheet already. It is what we will be accomplishing in this chapter. All right, so now let's go ahead and take a look at slide 3. These are our critical materials, okay? And what this ends up being really, really important in engineering because critical materials possess unique chemical and physical properties that allow them to play vital roles in technology. And that ends up being really important because they also end up being somewhat, sometimes they're hard to find. They are prone to disruptions in availability. Sometimes they are not the safest things to remove from the earth. For example, like with lithium. Okay, this is considered a near critical material because it's used in lithium batteries that power a whole bunch of different things. And but then it's also hard to get. Okay, so one of the big things that engineers and chemical engineers and engineers of all types are trying to do is basically think about, okay, how can we replace critical materials? And I have some interesting stories for that when we start talking about carbon fiber, which is a really great way of doing that. Okay. All right, so now let's take a look at a few things. First of all, the scientific method. In the scientific method, our first thing here is going to be that we are going to be making observations about nature. And these observations are, they can be qualitative or quantitative. Okay, so qualitative observations, qualitative observations might be things like color, okay, texture, things that we can describe. In a quantitative observation, Quantitative, think quantity. So this is going to be data with numbers is kind of like how I like to say that. Data with numbers. So it might be a specific value. And that's our quantitative information. Okay. Our next piece here is to derive a hypothesis. Okay, or build a model. And I like the idea that a hypothesis is sort of an educated guess, or a possible explanation. So a hypothesis is one of those things that we actually have to put some thought into it. Sometimes it can be a form of a question. All right. And our last piece in here is to construct experiments to bolster or refute the hypothesis or model. And then my most important thing here is repeat. Okay. You must repeat this entire process many, many times in order to make sure that you have repeatability. Okay. Can you get your same data again? So now let's take a look at our next step here. In the study of chemistry involves three levels of understanding or three perspectives. Macroscopic are things that we can see, touch, and interact with. So some examples of that might be people, a desk, rocks, trees. Okay, so these are all things in our world. Okay. And now we have microscopic. Microscopic is basically just talking about things that are too small to be observed without special tools. Okay. And that will be, things that you might need a microscope to see. You might need, like an electron microscope also to see things that maybe you can only observe through measurements. And then symbolic is basically a representation of the world. Okay. So, for example, if we're going through this, let's say that macroscopic might be a diamond. Okay. And diamond is formed with these tetrahedral shapes. Um, okay. And it's these perfect tetrahedral carbon. And okay. Now, symbolic, our representation of the world, this might be C diamond. Okay. So this is what it really looks like in it's an interlocking carbon structure. C with the word diamond after it is our symbolic representation of that. Now let's take a look at the macroscopic perspective. This is slide 6, if you're following along. Okay. Matter is anything that has mass and can be observed. And we look at matter through two separate kinds of changes. Okay, so first of all, we have physical changes here. This is our first kind of change. Physical changes change the physical form, but not the chemical structure. Okay, so examples of physical changes could be phase changes. And a phase change means going from like solid to liquid or liquid to gas. That's a phase change. Cutting a piece of paper, if we take a piece of paper and cut it or rip it, that's a physical change because we haven't actually changed the paper. Another one might be something like dissolving sugar in water. And the reason that you might think that's a chemical change, but we're not actually changing the shape of the water. Okay, we're only or the sugar. We are just separating the molecules from each other, and then we can evaporate the water and get the sugar back again. And because the sugar hasn't actually changed anything. All right, our chemical changes now. Okay, chemical changes might be um, some other types of things. So it says it rearranges the way atoms are bound to each other. So we're all also going to see this when we talk about chemical reactions. Okay, so chemical changes are always going to be chemical reactions. We'll put a 2 here. Okay, and some examples of this might be basically anytime we burn something. So if we're burning wood or we're burning methane, that's a chemical change. The process of digestion within the body is a chemical change involving enzymes. Another one might be baking. When we bake, we're always using some kind of a leavening agent that creates a gas, so yeast or baking soda, sodium bicarbonate, that kind of thing. Okay. All right. Here we are now on slide 7. This is now we're talking about macroscopics. Okay. And in macroscopics, what we're looking at are we've got a couple of options for this. So, first of all, the physical properties in macroscopics are variables of matter that we can measure without changing the identity of the substance being observed. Okay. So, physical properties include mass, density, color, viscosity, hardness, and temperature. Okay. And of a physical property, so we're looking specifically at density right here, is that the density of an object is a ratio of its mass over its volume. Okay. And so right here, you could say density is equal to mass divided by volume. And that's what that means. Okay. And another example of what we're looking at might be something called malleability, the ability to be rolled or hammered into sheets and stretched. Aluminum metal has a high malleability. It can easily be turned into sheets or into wires or whatever it is that we're looking at. All right, now let's look. We're on slide 8. Okay, this is also still talking about macroscopics. Now, if we're talking about the chemical properties of macroscopics, these are determined by observing how elements are rearranged in chemical reactions. Okay, so what do we mean by rearranged? Okay, so here we have pure aluminum reacts with acids to form an aluminum salt. Okay, and hydrogen gas. And here, when we use the word salt, we mean an ionic compound. We don't just mean table salt. Okay. And so what's happening is that pure aluminum reacts with acids to form an aluminum salt. So we go from aluminum solid, we'll say, plus hydrochloric acid, and that's aqueous. And aluminum forms 3 plus ions, which means, so this is going to become, hang on, you will be able to do all this soon. Okay, so forms aluminum chloride, AlCl3, and this is still aqueous because our hydrochloric acid was aqueous, and hydrogen gas. Okay, and that's what that's describing. And then what I can do here is I can say, okay, well, I need actually, we're going to have 2 of those so that we can have 6 of those and 3 of those and 2 of those. Okay, and you will learn how to do all that later on. So looking at a few other things, we have combustion, and that's the ability of a compound to burn in oxygen. So it's your compound plus oxygen gas. Okay, and that's that. And then you will have corrosion, and that's the degradation of metals in the presence of air and moisture. And corrosion is also usually going to be plus oxygen and water, and it turns into something else. Okay. All right. And now we are on slide 9. Okay. and we're talking about the macroscopic perspective. Okay, still, this is our last one here, and we're going to describe 3 phases of matter, okay? Sometimes these are called states of matter. Okay, so first of all, solids have a fixed volume and shape. So they aren't going to change unless we make them change. They're going to stay as they are. Liquids assume the shape of the container, they have a fixed volume. So the volume is fixed. That means it doesn't change, okay? And the shape is variable. Okay. In gases, they occupy the entire volume or shape of the containers. So in a gas, the volume and the shape are variable. Okay. Microscopics. Let's talk about microscopics now. And we are on slide 10. Okay. So the microscopic or the particulate perspective. So a lot of times when we think about microscopic, people tend to think of microscopes. But in chemistry, we're thinking about more of on the terms of particulates. And that's a little bit different because in chemistry, you can't usually see your particulates or in a microscope because they're just too small for that. Okay, so in chemistry, we would say that matter is composed of minute particles called atoms, okay, that retain the chemical identity of the element they represent. All right, so an element is composed of atoms with identical physical and chemical properties, and you can find these on the periodic table, which you will all have a copy of in this class, of course. And these atoms make molecules. And molecules are groups of atoms that are held together by attractive forces to form discrete units. Okay, so some examples of molecules might be H2O. Okay, it might be CO2. Okay, and these are examples, maybe C6H6. We have water, carbon dioxide. This last one is benzene. And each one of these molecules exists as a discrete unit. So your water actually looks like this, full stop. Okay. And that's different than compounds. Compounds are groups of atoms that are held together by forces. And compounds can be molecules, but they can also be ionic compounds that exist in lattice structures and not discrete molecules. And we'll get to that more in a bit. Okay. Here we are on slide 11. And let's take a look at a couple of other things. Okay, so we had physical changes and chemical changes for macroscopic, and now what we're going to be doing is we're going to be looking at them for microscopics. So in the microscopic, let's take a look at what's actually happening. So during a physical change, the chemical composition does not change. So this is an example. This is the same type of thing we looked at before, where we said going from a gas to a liquid or a liquid to a gas. And basically what's happening is that here you have your macroscopic view. This is what you can see, but this over here is what's really happening. So when it's a liquid, it looks like this. Okay. And as we heat it and boil it and it becomes a gas, then it looks like this. So our actual molecules have not changed. Here we are on slide 12. Okay, and let's take a look at this next one. So now we're looking just at the microscopic perspectives of a chemical change. And in a chemical change, first we have water, okay? And then after the reaction, we have hydrogen and oxygen. And this is a chemical change because what we've done is we've actually converted these two to different things. All right, slide 13. Last, we have a symbolic representation, and we're going to be using this quite a bit in this class because this is how this is how we're going to be talking about chemistry. All right, symbols are used to represent atoms, compounds, and reactions. So, for example, pure aluminum might be reported as Al. This is the symbol from the periodic table. Now, let's create an ionic compound, such as aluminum oxide, and that's going to form Al2O3. Okay. Now we can have molecules, and one example of that is diatomic oxygen gas. Oxygen gas only exists diatomically, so when it's by itself, it's going to be O2. And then the reaction between aluminum and oxygen form aluminum oxide would look like this, where you have solid aluminum plus gaseous oxygen forming solid aluminum oxide. Okay. Now, you can also do this with something different. We could work perhaps with saying, okay, well, we have hydrogen gas. Okay. Plus oxygen gas forms liquid water. Okay. And that's another option for this. Okay. So then the words for this would be hydrogen gas plus oxygen gas forms water. So now let's talk about making some observations. Okay, and then we'll go ahead and take a break and we'll come back and do more math. Okay, so our observations in science, first of all, let's see here. Let me put a slide number up here so that you can match it. Observations in science, we're looking at slide 14, and we're going to be talking about a couple of very specific things. One is accuracy, and one is precision. And this is not always discussed with something that you would expect from kind of a layman's terms. So first of all, accuracy is how close the observed value is to the true value. And precision is how close repeated measurements are to each other. So in this first one, we aren't precise and we aren't accurate because we've got a point here and here and here and here and here. But right here in the center is where we want to be, and we're nowhere near it. Now, the next one, we want to be here in the center, but we're all off here to the side. So we're not accurate, but we are, however, precise. Okay. And this next one, you can see that all of your points are clustered right in here. So you're both precise and accurate. So I'm going to see how close the observed value is to the true value. Okay, so let's say that we have a true value equal to 2.50 micrometers or microns. Okay. Something that, so now let's take a look, let's say that we have 3 trials. Okay, so trial 1 is 2.45 and 2.48 and 2.51. And trial number 2 is 2.0 and 2.3 and 2.9. And that was trial 2. Trial 3 is 2.91 and 2.81, 89 I'm looking at my notes, and 2.93. Okay, so here's our three trials, and let's take a look. What does this mean? Okay, so this first one, remember that our target or our true value is 2.5. Okay, so these are all very close to 2.5 and to each other. So this is both precise and accurate. This one. We have 2.0, 2.3, 2.9. These are all very far away. So very far from 2.5 and far from each other. So this one here is neither precise nor accurate. This one at the bottom, we have 2.9, 2.89, and 2.93, and these are close to each other, but not to the target. So this would be considered precise. Okay. All right, on our second part of this one, and this is slide 15. Okay, our observations in science. So let's take a look at a couple different types. Okay, so we have random error. Okay, and in random error, measurements might be too high or too low. Okay, there's noises at my house. All right, in random error, these measurements might be too high or too low. And the variations are usually due to equipment limitations that are throwing things off. And an example of random error from that previous slide might be that deposition that was 2.0, 2.3, and 2.9. That would be a random error creating neither, it's not precise or accurate. It's pretty difficult to fix in engineering. Our second option here is a systematic error. And a systematic error makes measurements that are consistently too high or too low. They talk about the presence of an impurity, but I've also, in my engineering experiences, seen this due to an equipment issue. And it can be an equipment issue, it can be an impurity, but this is usually pretty easy to fix. And an example of that would be from the previous slide, 2.91, 2.89, and 2.93. Okay, so this is precise, but not accurate. And those are usually easier to fix than a random error is. All right. Okay, so at this point, I'm going to go ahead and pause this and we will return for slide 16.